part C. Part C.3, examples of asymptotic notations, part 2. First, we continue our example number 8 from C.2. We need to show n factorial belongs to little o of n to the nth. This one, pretty hard. The reason is that n factorial. But good thing is we have that Stirling's formula. So we have upper bound, lower bound estimate for n factorial in this one. So now the question, how do we use the upper bound, lower bound estimate of the n factorial? The question, we need to compare n factorial with n to the nth power. Then that means we need to take the limit of the ratio of these two functions. Little tells us we should show that limit equals 0. Then we are done. All right, so let's consider that ratio first. The ratio, use the Stirling formula after simplification. So we have the, two functions bounded below and bounded upper, right? Below, higher, So these two functions, above, okay? All right. So then, when we take the limit, so we have this limit inequality, right? Here. Pay attention to the little things. Our original inequality, strictly less than. But when we take the limit, you need to add an equal sign. The limit, you may get that equal case. Now from the calculus, you should have that little thing, in your knowledge. All right. Now let's consider these limits. We can say the limit equals 0 for the left function. And the right function limit also goes to 0. Why? The reason pretty simple. Remember, we did one example, C.5 before. In that one, we have n to the d belongs to little of a to the nth. Can we apply this result directly? N to the d equals 1/2, right? And a equals e. How about that? When you apply this result, then we have that limit equal to 0. Lower bound, the limit equals 0. Upper bound, limit equal to 0. What is in between? What is the limit between upper 0, lower 0, in between? Nothing else. Only 0 you can take, right? You have no room, no other thing you can choose. Only 0 you can choose. So that one, we call it in calculus, two names for that result. Squeeze theorem or sandwich theorem. So we apply that, either squeeze theorem or sandwich theorem. We have that the middle limit equals 0. So we proved n factorial belongs to little of n to the nth power. So you can see how many results do we need? Stirling's formula. Okay. Then squeeze theorem or sandwich theorem. Okay. Then another result, that result. Okay. So you can see, put these three pieces together, then we can solve this problem. Yeah. All right. So that is number 8, example number 8. Then the last example, number 9. For each of the following functions, indicate the class big theta of g of n. Yeah. All right. The function belongs to, use the simplest g of n possible in your answers. Yeah. So let's look at these questions. A, this function. B, this function. C, this function. Pretty complicated. Yeah. D, this function. Okay. E, this function. Okay. All right. So let's look at this one by one. Yeah. For A, pretty easy. So how do we solve a question like this? We only look at the dominant term, n squared. Plus 1, too little, we can ignore. Yeah. So if you use n squared raised to 10th power, so your g function becomes n to the 20th. Yeah. So big theta of n to the 20th. Yeah. So that's the class you want to choose. Yeah. B, this time we select the dominant term. We ignore the minor terms. Yeah. So all other terms, minor terms we can ignore. All right. Yeah. So the dominant term, we take the square root. And we can also ignore the constant part, 10. We don't need to use 10. Okay? Yeah. When we consider growth function, we can skip that leading coefficient. All right? Yeah. So n squared taking square root, that's just the n. So our big theta class g function is n. Yeah. So that's the second one. The third one, E, yeah, because E easier. So let's do E first. All right. Let's do E first. Yeah. E pretty easy. The floor function, right? The floor function, we know the original function, we find the nearest integer from below, right? Yeah. So that difference less than 1. So that difference too small. So you can see we can still use the log function. Log function, right? Yeah. Here, so we can use g function log. Yeah. All right. Yeah. This LG, this log LG in our textbook, our LG means base 2. Yeah. If in typical math books, that LG probably using base 10. In math, most commonly use the base 10. Other than E, right? Natural log. Other than E, most popular base 10. But in CS, computer science, other than E, probably including E, right? The most popular base is 2 in CS. Yeah. All right. But here, no matter what base it is, we can, we can easily change that. Yeah. So later we will see that. Yeah. All right. D, so you can see the dominant term. There are two terms. Exponential function with base 2, exponential function with base 3. But definitely the term with base 3 dominates the other one. Okay? Yeah. So you can see if we choose big theta class, that should be big theta of 3 to the nth. Because that minus 1, just some constant, right? So minus 1, we can skip. The reason is 1/3 times 3 to the nth. So that's just a constant. The minus 1 exponent part can be translated to that fractional constant. Yeah, so we can skip. Yeah. Yeah. And power of 3 definitely dominates power of 2 function. Okay, yeah, so that's D. Then the last one, C, the last one. So which term is dominant? Which term is dominant? Okay, yeah. The second term is dominant, not the first term. The first term much smaller than the second term. Why? Second term, you have the square, right? Yeah. And although the first term, the log function part, there are, exponent 2 here, but that one can be converted to leading coefficient 2. Okay? Yeah. So that is not big. That's just a constant. Yeah. And log n over 2, by property of logarithm, log of n minus 1. Here, the base 2, we use base 2. Okay, yeah. So you can see, yeah, the log part, same category, yeah, multiple of log n, right? Same category. But the polynomial part, n squared, and the second one is, the second one is higher, yeah, larger. So the big theta class, n squared log of n. N squared log of n. Yeah. All right. Next, I may like to refresh this formula, change of base rule. Yeah. Because when we look at the log, frequently we need to consider the base, different base numbers. But actually, with this change of base formula, we can do conversion easily. So here, let me put the change of base formula here. Original base A, B, yeah. Then we can change to C in this ratio form. That's the change of base formula. Later, in our exercise questions, we will apply this change of base formula. All right, yeah. So that's, everything for part C. So we finished part C right here.